So this fair price is a price where you'd be indifferent to buying or selling the bet, right? Now, because these are disjoint events, probability laws require that the probability of the two is equal to the sum of the probabilities, and if you violate these, then someone can mint money off of you, right? Because they can, if you say that the probability of the joint event is less than the sum of the two, someone can buy the joint event and sell you both and make money, and presumably you don't want to be taken advantage of that way. Any other violation that you make of the laws of the probability calculus can be Dutch booked in some way like this. Dutch book means a way to make an arbitrage plan. So a reasonable person not only has these probabilities, but uses them in a very specific way. And before I wasn't mentioning that this was my wife, but I think I'll just mention that it's my wife. So my wife went down to a meeting to interview a politician in Bogota. And the politician started asking her questions about her loyalty to me, basically saying things like, you know, have you ever considered cheating on your husband? Would you ever, if Brad Pitt wanted to have sex with you, you know, would you have sex with him, and so forth? So my wife got a bit freaked out, and she said, well, there's basically two reasons why this guy could be doing this. One is he may be trying to hit on her. Another one, and in that case, she wanted to rebuff him. She didn't want to, you know. The other thing he may be doing is he may be trying to test her morals. He may be trying to see whether, you know, she is, a morally loose woman, in which case she wanted to pass the test, right? So either way, she wanted to respond in the way that was, you know, loyal. And therefore, clearly, regardless of which interpretation is correct, the right thing to do was to respond loyally. So in the ignorance of which interpretation was correct, she made the correct choice, which was to respond loyally. And so this reasoning is known as Savage's sure thing principle, which is that if alpha is preferred to beta, if you knew that E occurred, and alpha is preferred to beta if you knew that not E occurred, then you should do alpha rather than beta regardless. And basically, these principles, beliefs in probabilities and the sure thing principle, imply that your utility for some action can be represented as the sum over all the states of your utility in that state for the action. So sure thing principle basically, and I'm not going to go through the proofs, implies, along with some weak technical condition, that you can represent everything as a sum across states of the utility you get in that state. And then the existence of probabilities means you can bring the probabilities outside of this, and so basically you have to be maximizing your expected utility. And in fact, you can even derive the probabilities themselves from the sure thing principle, along with some technical conditions. Now, Savage's proofs are quite involved, and I'm not going to go through them, but this is the basic idea. So, again, we have some flexibility when we think about these expected utilities in terms of the units. That is, the von Neumann-Morgenstern utility index here is semi-cardinalized. That is, it's only defined up to a level and a scale. So we can say that people have an arbitrary level of utility, and we can multiply their utility by anything, but otherwise it's got to be tied down by their attitudes towards risk. And as before, we could choose to cardinalize it fully to compare across people. But the basic point I'm trying to make here is that a rational, reasonable person, if you believe that the sure thing principle, the way my wife acted, was sort of the only one rational way to act, then you should believe anyone who doesn't maximize expected utility is unreasonable or irrational. So, nevertheless, there have been some very important objections made to maximizing expected utility. And the first one is what's called Ellsberg's paradox. And this is probably the most fundamental. The idea is, imagine that there's an urn with 100 balls, some red and some black. And you don't know how many balls of each color there are. One ball will be picked at random, and you have three choices among what you could get. You could either get $101 if a red ball is pulled. You could get $101 if a black ball is pulled, or you could get $100 if you get heads on a fair toss of a coin. Maria, which one of these would you choose?
Either one or two.
Either one or two. Which one? Well, you say you're indifferent between one and two. You're indifferent between one and two. Does anyone have a different preference than Maria does? Yeah. You choose three. Would you choose three too? How many people would choose three? Well, the majority of people would choose three. Okay. So most people go along with that. But note that this is inconsistent with probability. Why? Because you have to have some probability on red being picked and some probability on black being picked. If red is greater than black, you should choose red. If black is greater than red, you should choose black. And if they're equal, then you should choose either of them. But the point is, you should never choose the third option, right? Because there's no alignment of the probability such that that's the right thing to do. Yeah.
But you have no idea how many of each balls you have. So like you don't have.
I know, but you have to assign some probability to it. That's what Bayesian is required.
You don't have a measurable space. You have no ways of assessing which is best or not.
Okay. Look, I know you have no way of assessing, but Bayesianism doesn't rely on the way of assessing it. It says you have to assign probabilities to every event. You have to assign a probability to the red ball being chosen, and the rest of the probability is assigned. And that's just what, I mean,
maybe you're like inherently thinking of a measurable space. We are only interested in assigning probabilities to things that can be assigned probabilities. Since we have no idea how many balls there are, we can assign probabilities.
Okay, so your reaction to this is that you don't think you need to be a Bayesian. That's literally all you're saying. A Bayesian assigns a probability to any event that can occur. These are clearly events that can occur. You have to assign a probability to them. If you're a Bayesian, but maybe you're not a Bayesian,
so
that's fine.
Required to be measurable. Like it doesn't have to be in a sigma algebra or something like that. Or
By the way, this is easily in a sigma algebra. There's only two events here: red and black is full. But anyway, but forget about that. Like this clearly is a sigma algebra. But that has nothing to do with the analysis. I mean, the point is that you just have to assign a probability if you're a Bayesian. You don't have to be a Bayesian. That's fine. I'm going to try to convince you that that's completely crazy not to be a Bayesian. But you can claim you're not a Bayesian if you want to claim to that. And I'll try to show you why that's completely irrational. I think even by your own standards in just a moment. So, okay. But anyways, you can continue to believe that this is clear. Some people have taken that interpretation. I'm going to argue that that's a crazy interpretation to take. But nonetheless, let me see if I actually have it otherwise. Yeah. Good. Okay. So another famous challenge is what's called the LA paradox. This is not a challenge to the existence of probabilities. It's a challenge to expected utility maximizing. So two experiments. The first choice is you get $1 million. In the first experiment, you have two choices. You can either get $1 million for sure, or $5 million with 10% chance, $1 million with 89% chance, and nothing with 1% chance. How many people would choose option 1? Please raise your hands high if you're going to raise your hand. Okay, that's the majority. How many people would choose 2? That's probably a slight minority. Okay. Most people... Millions, yeah. Sorry, 5 million. So how many people would choose 1 now? And how many people would choose 2? Majority choose 2, but some people still choose 1. Well, in reality, in experiments, almost everyone chooses the first option. In the experiment 2, the choices are 1% chance, 11% chance of getting $1 million, 89% chance of getting nothing. And then in the second option is 10% chance of getting $5 million, 90% chance of getting nothing. How many people would choose the first option? Nobody. 0 people. Okay. How many people would choose the second option? Everyone. Okay. So most people choose the second option in this case. Note that this is inconsistent with the sure thing principle if you chose the first option in the first case, because if we define the event E to be the 89% chance that in the first experiment you got $1 million, and then the second experiment simply makes this 89% chance event into the getting nothing, it doesn't actually change it doesn't change anything. It just makes an event which was common between the two things equal to 0. So what that means is that if in this rest of the probability you preferred this over this, then when you add in that other event, you also have to prefer that over that. Because it's literally just a short thing principle, right? Because you were indifferent between 0 and 0 in one case and 1 and 1 in the other case, 1 million and 1 million in the other case, and so short thing principle said you have to, if you prefer in this case, also prefer in the other. So your preferences should be consistent between these two things. So there's three common responses to these types of results. And Maria, what are the three common responses that people have? To these experiments, to these paradoxes.
I would say that if you ask me about this when I don't have the actual money in front of me, I'm going to answer differently than when
Yeah, so that's one very common response. So people don't actually behave this way when they are faced with real choices in the real world, and this is that it's a product of the artificial hypothetical set situation. And John List has done some great work on this, and I think has shown that in some cases that's true. But there seem to be some real-world cases when people do continue to behave in ways like this. So this is certainly not everyone's reaction. My reaction is that these things are just people making mistakes. And that they might sometimes continue to make mistakes in the real world, but still they're just mistakes. They're people being stupid, basically. So this is my view about Ellsberg, so let's think about it. Imagine that you could generate a coin flip, right? And then what you have, someone offers to sell you the following thing. For 50 cents, I will flip a coin. If it comes up heads, I'll put the money on the red for you. If it comes up tails, I'll put the money on the black for you. Now, you are strictly better off, right? Now, your thing depends only on the flip of a fair coin, right? And you have $150 if you get the right flip, rather than $100. So you're strictly better off under that. And yet what you're saying is then if someone tells you the outcome of the flip of the coin, suddenly you're worse off now, regardless of which way it comes up. So that says you would prefer not to know a piece of information because it turns this objective uncertainty, which, I don't know your name, what's your name? Andre? Andre was comfortable with, because it's measurable or something like that, into this unmeasurable uncertainty. And suddenly now you're strictly worse off because you have a piece of information, even though there was nothing strategic or whatever. So that seems completely crazy, right? In my view. And in fact, we open you to a Dutch book, right? Because what people could do is they could, have you buy one of these things, so now it depends on the coin flip. Then the coin flip comes up. Oh shit, now I'm depending on the, unmeasurable uncertainty. Well, someone else sells me a coin flip. Okay, now I'm better again. But now oh no, crap, I've got to do it again, right? So that seems just like totally nuts in terms of behavior. So my view is that what's really going on in this situation is people think, or they're using a heuristic that's based on the idea that the experimenter is hostile to them. That if they commit to either red or black, the experimenter's going to be like, oh, I can go screw that person by making all the balls red. I can go screw the person by making all the balls black. And that they're not really thinking about the situation as posed. They're thinking about this other situation where the other person is hostile. And I don't think we really respect someone who actually understood the thing and still committed these types of preferences, but it relies on this crazy thing of not wanting to know information. Now the third response is the one that Andre initially had, which is that it's reasonable not to be an expected utility maximizer. And there's a long line of literature, huge line of literature in decision theory, which is based on this idea. And I'm extremely skeptical of this literature. But anyways, other people are not. Other people work on it. Yeah.
So is it the same to fail the Ellsberg paradox in the error and not to maximize expected